Okay, so I think we got to the last lecture of this course, so it's been really a pleasure for us. And in the last lecture, I would like to talk about some applications and the next steps in geometric deep learning. So allow me to again overview the structure of this course from the beginning. So we talked about the geometric principles that underlie deep learning, and then we looked at their specific implementations, and the key concept that unifies deep learning according to this course is this concept of symmetry that I showed in my first slide in the beginning, and I would like to show it in the last lecture as well. This quote from Weil that symmetry is wide or is narrow is one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. And we try to comprehend deep learning through this lens of symmetry, what we call the geometric deep learning. And we've seen instances of this principle on multiple structures, whether it's grids, groups, graphs, and manifolds. And we've seen that basically you can derive from these basic principles some of the popular architectures such as convolutional networks, graph neural networks. Peter in his lecture before showed how to derive gated recurrent networks and LSTMs, and before 2 and 3 lectures before we discussed mesh CNNs and intrinsic learning on manifolds and meshes and geometric graphs. So I guess the obvious question is what's next, right? So somehow you can judge about the quality of a theory or a framework by its predictive power, and you can argue basically whether this framework is just a pedagogical instrument to unify and to teach in a better way deep learning, or whether it will evolve into something more substantial. And of course, we believe that it is something more substantial. So what I would like to show you today is maybe a few thoughts about where I and others believe this field will go, and what are the interesting research directions and open problems. And I based it roughly on a blog post that I wrote in the beginning of the year by interviewing some prominent researchers in the field of graph ML and geometric ML, and also people that use these methods in their research in different fields. And I will quote some people from this post. So let me start with Will Hamilton, that I guess doesn't need any introduction for people working with graph neural networks. He is a professor at Mila, and he is one of the authors of the Graph Sage, which is one of the first scalable implementations of graph neural networks. And he said that last year saw the field of graph ML come to terms with the fundamental limitations of the message passing paradigm. And this is also what we discussed in depth in Peter's talk. In his lecture, he discussed the relation of graph neural networks to the Weisfeier-Lehmann graph isomorphism test, and what kind of graphs, what kind of structures would not be detectable by this message passing. So it is interesting that it was, in a sense, an easy way to find this connection between graph neural networks and the Weisfeier-Lehmann algorithm. Actually, if you look at the precursors of graph neural networks, they came more or less from the same domain. Actually, Weisfeier and Lehmann themselves were inspired by problems in chemistry. And so it's not, this link is not exactly very surprising. And in a sense, it's something that is almost on the surface, and it's easy to take advantage of it, but it has its limitations. So the question is, what could be used instead of message passing? And here we believe that message passing is still a very powerful paradigm, but maybe we should use some other structures. We can apply it to exchange information on maybe slightly more exotic constructions. And there are several papers in the past years that try to go in this direction. Well, here, of course, I'm biased. I show a picture from our own work. So this is collaboration with the group of Pietro Leo at Cambridge, the work of Chris Bodnar and Fabrizio Frasca, who is, I think, giving a seminar on this topic later today. So I don't want to steal his thunder, but basically we developed Weisfeier-Lehmann-like schemes for higher order structures, in particular for simplicial complexes. So if you think of meshes that we discussed when we talked about manifolds as discretization of continuous surfaces, they, technically speaking, are what is called cell complexes. So in addition to nodes and edges, you also have higher order structures such as triangles. And you can generalize it further. So at the next level, three-dimensional simplices will be tetrahedra and so on and so forth. And cell complexes are even more general structures. So they basically they're implementation of a certain discrete topology. And you can show that you can, by doing this kind of higher order message passing, you can get architectures that are strictly more powerful than traditional message passing in neural networks. And there are many interesting deep theoretical results in topology, as well as some interesting applications, for example, in computational chemistry. And this is probably something that you also explored a little bit in your practical work, is that in molecules, you have a lot of structures that go beyond graphs. Actually, chemists don't think of molecules as graphs. They think of it, they think of them as some combination in certain way of primitive structures. And cell complexes are one way of capturing these structures. Then there is an interesting direction as well. So this comes from the work of Kyle Cranmer from NYU. I think it was collaboration with DeepMind. And the idea is that you can, instead of using generic message passing, you can make this message passing symbolic. And in particular, they were considering physical systems, multi-particle systems that interact, and the interactions are captured by a graph. And you learn generic message passing neural networks, usually generic message passing functions. Usually, these are small multilayer perceptrons, and then you regress symbolic equations from them. And replacing these generic message passing functions with symbolic equations gives you two things. First of all, better generalization, but second, you get the laws of physics from your problem. So, and I think it's good to look at it in perspective. So I mentioned also in the beginning, in the introduction lecture, Johannes Kepler, the German astronomer that studied the crystal structure of ice in his work on six-cornered snowflake. But he is also famous for the Kepler's law that took him his entire life, essentially, between 20 and 30 years of analyzing observational data to come up with a formula that explains the orbits of the planets. Nowadays, with this kind of system, you can do it maybe in a few minutes or maybe even seconds. So it's pretty amazing how science has progressed. And this is related to a more general category of machine learning methods that is called algorithmic reasoning. And I think Petar mentioned it in his lecture as well. And when it comes to abstract data such as graphs, we do have a very established way of working with them, right? So if you want, for example, let's say in Google Map to predict the travel time from one point to another, you could apply something like the Dijkstra algorithm that computes the length of the shortest path in a graph. So this is standard techniques that are used in routing and in geographic applications and so on. And if you compare neural networks to graphs, to algorithms, then one thing that you see that obviously algorithms are extremely explainable and they generalize perfectly across different data, but they don't generalize across tasks, right? Whereas neural networks, they kind of generalize to data, but not given for granted. They are not necessarily explainable, and in many cases these are just black boxes, but they do generalize across tasks. So it's not uncommon, for example, to train let's say a convolutional neural network on ImageNet and then apply it to a completely different zoo of images. So I think even in the reconstruction of the black hole event horizon, there was apparently, from what I read, a convolutional neural network that was pre-trained on natural images. So algorithmic reasoning tries to take the advantages of both worlds and fuse them in a formal and rigorous way. So there is another interesting topic that is especially of interest in biological sciences, and this is causal inference. And what I show here is also a recent paper where they try to reconstruct causal graphs. And the typical scenario that you see here is some gene expression in healthy and diseased cells. And you want to understand what causes the disease. So the way that you can describe it on the cellular level is this gene regulatory network, where you say that if I have, for example, a gene that is expressed or not expressed, that this is what causes the disease. And you can try to build this graph that explains actually the mechanics of how this disease works, or how a therapy, for example, works. So this is also very important. And of course, in many cases, we must have this interpretable result in order to understand and take action. Related to this is also the field of knowledge graphs, where I have these heterogeneous graphs, for example, that tell you relations between different objects, very common again in biological sciences and medical sciences. So here you can see, for example, a graph that describes different symptoms and treatment of pneumonia, and a biological graph on the right that relates different mechanisms of different diseases and drugs. So another interesting trend as well. So this is Thomas Kipf from the fame of the GCN architecture that we discussed in the recent lecture. So he's currently at Google. So he notices this trend in the GraphML community is the separation of computational structure from the data structure. And we mentioned it a little bit, and I think Peter also referred to it in his lecture, is this idea that you don't necessarily need to stick to the input graph to do your message passing. And here I'm showing a figure from a paper from the group of Stefan Günnemann from Munich, where they said that if you take a graph, you can embed it with some diffusion process, and then rewire the graph. So just connect the nearest neighbors in this embedding space. And on this new graph, you will get better performance. So the paper is called Diffusion Improves Graph Learning. So they show that on a wide variety of tasks and graphs, this kind of rewiring is beneficial. And there are many reasons why this is good. So there are also recent papers that look at the phenomena of over-smoothing and over-squashing in graphs. So these are deep and probably not completely understood problems. But I think it brings up an interesting question, is actually, when we talked about graphs and continuous spaces, somehow there was this deep disconnect. So graphs are discrete, right? And in continuous spaces, we could say that okay, I can discretize this space in many different ways, but somehow it describes the same thing, right? So if you think of meshes, for example, that discretize continuous surfaces, there are a zillion different ways I can mesh a continuous smooth surface. I can still say that it's the same surface, right? Up to some approximation. So there is an interesting branch of geometry that is called network geometry that brings together this field of differential geometry and graph theory that tries to think of graph as a discretization or a sampling of some continuous space. And there are deep results. For example, you can show that social networks, or what is called scale-free networks, where there is this phenomenon of a small number of degrees of separation, can actually be obtained from sampling of a space with hyperbolic geometry. So if you remember again the first lecture, when I mentioned some of the non-Euclidean geometry models, so this was the first one, the negative curvature space of Lobachevsky, the geometry of hyperbolic spaces. And there is an interesting dimension to it as well that can relate the question of graph rewiring and how to choose the positional encoding for the graphs, right? So this is also something that we mentioned, and this is through the lens of diffusion equations. And this was our recent paper at ICML that we did at Twitter. And the idea is that you can interpret graph neural networks as discretized diffusion partial differential equations. So we call these neural PDEs. And each layer of a graph neural network, or a certain architecture of graph neural network, can be interpreted as a step of an explicit solver, what is called forward Euler explicit scheme. And there are many other solvers that exist in numerical analysis, and we show that you can use better solvers with multi-step schemes, or, for example, with adaptive step size, or even implicit solvers that invert the diffusion operator. So it is interesting because in this case, you don't really have any more the notion of layers and depths. You have the notion of diffusion time. So you have some learnable parametric diffusion equation that you try to learn from a specific task, and then of course, the question of which graph to use is a little bit superfluous, because you can think of it as a form of discretizing your spatial derivative. So if you think of a diffusion equation that contains the Laplacian operator, right, as I showed when we talked about manifolds, there are many ways you can discretize this Laplacian. And this is a kind of intuition that we are trying to pursue. There are many interesting deep links to differential geometry. So in differential geometry, people like diffusion equations. So some classical result, for example, what is called the Ricci flow, which is diffusion equation on the Riemannian metric on the manifold. And if you're familiar with the Poincare conjecture, this kind of instruments were used to prove the Poincare conjecture. So that was the groundbreaking result of Grigori Perelman. It is interesting to look also at dynamic graphs, because in many cases the graphs are not static. So if you think of social networks, so these graphs change all the time. What is characteristic is that different kinds of graphs, or different portions of the graph maybe, or different structures of the graph, change at different frequencies. So if you think of a network such as Twitter or Facebook, the follow graph, basically the social relations between users, are typically not updated that frequently, but the engagement graph, where the user like or retweet content, are much higher frequency. So there are already existing models that try to generalize graph neural networks to this setting when the graph is not actually a static graph, but it's a stream of asynchronous events that add or delete nodes or edges. And again, here I show a figure from a paper that we did at Twitter last year. So another interesting direction, generative models. So you're probably all familiar with GANs, right? So here is a figure. I think this is from Goodfellow's talk on the progress in this field, how GANs became significantly better over just a few years in generating, for example, human faces. It is much more difficult to generate graphs. One of the issues, and there are multiple issues that complicate this problem, but one of them is that if you think of an image, we have canonical order of pixels, right? So one of the typical losses that you have in these architectures is reconstruction loss. When I have my input image, I do something to it, right? So I encode it in some latent space, and then I decode. And I can compare the input to the output. I can tell that it's similar or not, right? I can just subtract the two images and take a norm. With graphs, I input a graph, I do something to it, I output a graph, and now what? How do I compare them? We don't have a canonical order. And one interesting field of applications is the computational chemistry, where you can try to generate new molecular graphs, and there are a lot of these potentially, and you want to understand first of all, how to generate these graphs, and how to even to evaluate whether these graphs are interesting and meaningful. So in chemistry, again, people don't think of graphs as nodes and edges, so they try to think of them as some higher level structures. And this is the paper from the group at MIT of Tomi Yakola on junction tree variational autoencoders, one of the methods for generating molecules. Another important topic. So this is what one could probably fairly say that has been driving many fields in computer vision and machine learning, is the availability of large and standardized data sets and benchmarks. So some people, of course, complain that a lot of works just increase by epsilon some criteria and some benchmark and become a winning paper. But it is important indeed. In this field, just a few years ago, everybody was publishing results on their own data set, and it was very difficult to compare different methods. So availability of standardized evaluations such as Open Graph Benchmark at least makes it much easier to compare to existing state of the art. It doesn't mean, I don't necessarily think that achieving state of the art results on a benchmark or multiple benchmarks is really the goal of research in this field, but it's still important. There are multiple industrial applications, and well, probably too many to put on the slide. So here I just mentioned one of them. So that was recent work from Google that used graph neural networks for better placement of components on chips. And as you know, designing semiconductor chips is a very difficult problem. So these are combinatorial problems of placement and routing, where you put different components in some optimal way. And graph neural networks appeared to be more efficient in this task. They were used in conjunction with reinforcement learning, and there is an entire interesting field of relating graph neural networks to basically as a way of solving approximately combinatorial and NP-hard problems. So there was an entire workshop on this topic organized earlier this year at the IPAM at UCLA. And talking about hardware, actually the hardware itself on which graph neural networks run is not necessarily the best for graph structured data and for graph ML problems. And what happens in hardware is what is nicknamed the hardware lottery. It's a phenomenon where certain algorithms win not because they're ideally suited to solve a certain problem, but because they run well on existing hardware. And this magic conjunction happened with convolutional networks, that the architecture of CNNs and images is very well suited to the SIMD, single instruction multiple data architecture of GPUs that were developed for completely different kind of applications in computer graphics for rendering and texture mapping. So this lucky coincidence is quoted as one of the reasons why deep learning methods became so prominent, because you could run now a decade ago already very deep and very complex models very efficiently using graphics hardware. So there are multiple semiconductor firms that try to see where the hardware will go beyond GPUs, and one of them in particular is a unicorn based in Britain called GraphCore that develops a new kind of architecture they call the IPU that is explicitly designed for graphs, and many other companies look in this direction as well. So, as I said, there is a wild zoo of applications from self-driving cars to navigation. So Petra was actually involved in a product that DeepMind did with Google, improving the estimation of arrival time in Google Maps. So that was quite dramatic improvement, and this is already used in Google products. And there are many more interesting applications. So I don't expect to overview all of them, but let me mention some of those that I consider to be cool and important and exciting. So let me start with social networks. Well, maybe this is professional deformation because I work at Twitter, but in this domain, one of the key applications, of course, is recommender systems, right? So this is how social network companies make money. So they show you content, and they want you to ideally to look at content that is most relevant and interesting for you. So one of the early adopters for graph neural networks in the recommenders was Pinterest, a US company that is an image-based social network. And they adopted the graph sage algorithm that was developed by Will Hamilton and collaborators from the group of Yuri Leskowitz at Stanford, who also happens to be the chief scientist. So there are many other follow-up works from Pinterest itself, from other companies as well. So 2 years ago, Uber published a blog post where they showed how they use graph learning to power recommendation with Uber Eats. So with Uber, you not necessarily only take a car to go from one place to another, but you can also deliver food. And basically they have this recommendation system for different kinds of foods that you can order from restaurants. So this is another paper. This is AliGraph. So this is Alibaba, a Chinese company that is similar to Amazon. So they're selling products. And in this case, they developed a graph learning infrastructure that actually powers many of the applications of Alibaba. And in particular, recommender systems, which can be thought of as a kind of edge prediction. So you try to predict links between users and items based on their previous activities. And again, graph neural networks are prominently used here. Another interesting topic, and this is how I got to Twitter, is detecting of some malicious content, and in particular misinformation. And we try to do it from the way that news spread. So you often hear about so-called fake news, and there is empirical evidence that the way that fake news propagate on a social network differs from the way that normal content propagates. So we try to use graph neural networks to detect these kind of patterns. And together with my students, I founded a company called Fabula AI that was acquired by Twitter 2 years ago. And you can imagine that for Twitter, graphs are one of the core components in the one being content, another one different flavors and different types of graphs, whether it's the follow graph that connects users, whether it's engagement graph that connects users and content, and some other graphs that Twitter doesn't expose publicly. So I mentioned also some applications in vision and graphics, and this is related to our discussion about manifolds, right? With geometric data, you have multiple ways of representing your data. So of course you can think of it, for example, as volumes, and this might be useful in medical imaging where you're interested in what's inside. You might think of your data just as sets, maybe with some extra features such as normals and color, or as meshes, which are discrete manifolds. And for example, in self-driving cars, the natural representation of data that comes from LiDAR sensors is point clouds. So maybe point clouds with some extra information. You can also get orientations, normals, for example, from Doppler imaging and so on. And Uber has recently been using graph neural networks for self-driving applications, for example, for predicting trajectories of car in a crowded environment where you have multiple cars that drive in different directions, and you try to predict where they would go, and for example, if an accident is likely to happen. So I also showed in the first lecture this video of a 3D avatar that markerless motion capture that uses a 3D sensor. So that was technology that is now being used by Apple in their iPhone. But we've been working quite extensively in other groups as well on different flavors and different versions of geometric neural networks for solving different problems in modeling of humans, human body and human face. So here on the left, you see, I think it's the first instance of a mesh variation autoencoder that we use for shape completion. That's a paper from almost 4 years ago, and now there are much better results. And a more recent paper on face modeling. So in this case, the input, for example, can be a point cloud. And we also worked with modeling of hands. So in this case, the input is just two-dimensional image that is encoded by a standard CNN and then decoded by a mesh CNN that synthesizes correctly not only the pose, but also the shape of the hand. And we used it in collaboration with a British startup called Ariel AI to do these detailed avatars of humans with elaborate hands. And Ariel was acquired by Snap last year. So these are the guys that are behind it. So Yasos Kokinos is a colleague and co-author, and I was one of the investors in the company. So now you can already find their technology in Snap products. So here's another example of talking about exotic shape from X problems. So what you see on the right might appear as a poor reconstruction of the image on the left, but it's actually not reconstruction from image, it's reconstruction from DNA. So it is possible in some instances to recover the structure of a human face from genetic information. So you can imagine, for example, applications in forensics, where you can try to identify the suspect or a victim of a crime, or you can also think of maybe historical or archaeological applications where it is important to reconstruct the face of a person that lived in the past. I'm not necessarily saying that this is a solved problem. It's very complicated, and my collaborator Peter Klaes, who works on this in Belgium, they actually apply geometric deep learning techniques to the prediction of genetic syndromes that sometimes are manifested in certain facial features. So another interesting field of application is physics, and here I will quote Kyle Cranmer. He is a professor of physics at NYU and was one of the authors of the paper announcing the discovery of the Higgs boson in the Large Hadron Collider. And he says that it has been amazing to see how in the last 2 years, GraphML has become very popular in the field of physics. And I think the field of physics is very broad, so I will just give you a few examples. So this is the Large Hadron Collider. It's actually not the collider itself, it's a small part of the detector. So you can see a human figure here for scale. So this is probably the largest and the most expensive machine that humans have ever built. And you need these kind of large detectors and large equipment to accelerate particles to near the speed of light, and then at very high energy bump them together, and as a result new particles are created, and then you look for some interesting physics, some interesting particles that might have not been observed before. And that's exactly how the Higgs boson that was hypothesized theoretically was discovered in an experiment. So what you see here is this jet of particles that are generated by a collision event in the Hadron Collider, and graphs are a very natural way of representing these kind of structures. And indeed, in this field of experimental particle physics, they have been explored for a variety of applications. One of them, for example, is particle jet reconstruction and segmentation, when you have some readings from the different detectors, and then you try to reconstruct where the registered event in the detector, where it belongs from. So essentially, what kind of particle it originates from. This is the very basic pre-processing step that you need to do in order to understand, to make any order in this kind of messy shower of particles that is generated and detected in the collider. Another interesting problem is detecting actually events and detecting and modeling detectors. And what you see here is a different kind of particle physics instrument. So this is called the ice cube. And this is probably the case where the expression, the tip of the iceberg, can be taken literally, because this is a cubic kilometer of ice that is used as a detector. So it is carved into the ice shelf of the South Pole. And you can see here the Eiffel Tower, this little blob for scale. So this is the detector. So it has a different density of photomultipliers that pick up visible light, or what is called Cherenkov radiation, as a result of interaction of neutrinos. And neutrinos, as you may know, they are particles that are very elusive. So they probably, we are now penetrated by billions of neutrinos per second that come from our sun and other stars, and we never perceive them because they just pierce us and don't interact. And they're used in a novel kind of astronomy that is called multi-messenger astronomy, where you look for streams of neutrinos from distant objects in galaxies far away, and then you try to correlate it with some traditional astronomy. But for this purpose, you need to detect the neutrinos, and it's very difficult. That's why you need these very large detectors. And a paper that we did with Joan and his students back 3 years ago, we used graph neural networks to model the detector and classify the events in this detector. Basically, here you want to distinguish between background events and neutrinos that come from astrophysical sources that are very energetic. And the problem with this application, that you have a lot of noise. So the neutrino events are extremely rare, even with this huge detector. So another completely different application. So this was a paper from DeepMind last year, and they used graph neural networks for fluid simulation. So you have a large particle system that can be used to model, simulate fluids. And of course, there are applications besides physics, also applications in computer graphics, where these particle systems are used to model water, smoke, and anything basically. So the field of structural biology. Here again, I will quote one of the contributors to the blog post that I mentioned in the beginning, Bruno Correa, my colleague from EPFL. He's in charge of the lab doing protein design. And he said actually two things: that in 2020, exciting progress has been made in protein structure prediction, which is a key problem in bioinformatics. And ultimately, the chemical and geometric patterns displayed at the surface of these molecules are critical for protein function. So two problems, structure and function. So I don't know how much you know about proteins and bioinformatics, but so let me describe in 2 minutes what's all about, right? And why proteins are really a big deal. So sometimes people call proteins the molecules of life, and I think it's not an exaggeration because we don't know any other life that is not protein-based. Well, maybe we'll discover something on other planets, but on Earth, any form of life is based on proteins, from huge mammals such as elephants and whales to even something that is borderline life, such as viruses. They're all based on proteins. So the way that it works, our DNA, our genetic code, and of other animals as well, basically it's a long sequence of what is called nucleotide. There are 4 nucleotides that are encoded by these 4 letters, A, T, G, and C. And each triplet of such nucleotides contains an encoding. It's an encoding of an amino acid. So we have, well, hundreds of amino acids, but only 20 amino acids, what is called proteinogenic amino acids, that form proteins that can be synthesized by cells in our body. So basically what the cell does, it reads out this DNA. Well, it has to transcribe it into RNA that then becomes synthesized into amino acids. And here you can see a table of how different triplets of nucleotides are translated into an amino acid, into a basic building block of a protein. It's interesting actually why this particular encoding and not something else. I think nobody really knows, or at least I have never seen anyone knowing why biology or nature decided to encode amino acid in this particular way. So a protein is essentially is a polymer, so it's a large biological molecule that is built of small individual ingredients that are called amino acids. And these amino acids, under the influence of physical forces, they fold into complicated structures that give the protein its shape, and the shape is responsible for its function. So a good analogy that I like is this, I don't know if you're familiar, this snake toy, which is a one-dimensional structure, but you can twist it, and you can this way build many complicated 3D structures from just one-dimensional thing. And the problem of protein folding is predicting the geometric structure, this 3-dimensional configuration, from the sequence of amino acids. And this is a crucial problem, and it was hypothesized by Christian Anfinsen, who was a Nobel laureate in chemistry, that protein folding is entirely determined by the amino acid sequence, of course, in a given environment, so temperature, acidity, and so on. And this postulate was exploited for nearly 50 years with entire competitions that were established, similarly to competitions that are used in computer vision and machine learning, to try to improve the prediction of the structure of a protein given an amino acid sequence. And the moment similar to ImageNet that happened in structural biology was in 2018. So this is called the CASP competition, where a newcomer, not from a biological lab, so that was DeepMind with AlphaFold algorithm, that significantly outperformed all the other competitors. And it was a big gap compared to results in the previous years. And finally, last year, AlphaFold 2 achieved significantly better results that are already on par with crystallographic resolution of getting these structures from X-ray crystallography. Now, I should say that, well, this was definitely a major breakthrough. I should say that there are many complicated things in AlphaFold. So it, for example, it uses multiple sequences of proteins that are related evolutionarily. So as you know, we all evolve. So as a result, some of our proteins might change. So the sequence of amino acids might change. Notwithstanding these changes, still somehow the structures of these proteins tend to be the same, because the protein needs to work. Usually they're used as, for example, as enzymes that catalyze chemical reactions. And if the structure is not correct, then it simply doesn't work, and this organism cannot live. So it will simply not be born. And so there is some conservation of certain properties in these proteins. So AlphaFold, I think, really, if you think of just one example of an application that could motivate why geometric deep learning is important, it's this one. So we talked about equivariant message passing. So AlphaFold calls it invariant point attention. So it's a special kind of geometric attention network that is used for predicting the folding structure of proteins. So I would consider it one of the triumphs of these ideas. So I should say that this is a very fast-moving field. So just preparing these slides, I came across a paper from a person I know well, Mohamed Al-Kirashi, who is now in Colombia. So he was one of the competitors in the CASP-18 competition, and he didn't perform as well with his method that he calls recurrent geometric network, which is also implements some ideas in geometric deep learning, but it's a little bit more similar to LSTM with some geometric structures. So he underperformed compared to AlphaFold. Now, 2 days ago, they published on the bioRxiv a paper that I cite here, and don't take me by the word. I haven't read it. I just briefly skimmed through it. So they claim to have a single sequence protein structure prediction that doesn't use any protein evolution. So it's a combination of this geometric network and the language model for protein sequences that can predict the structure from a single sequence. And they claim that on some cases they outperform AlphaFold. So this is how fast this field evolves. And why proteins are at all a big deal? Well, they are everywhere in our body, whether it's defense mechanisms, so antibodies that act against pathogens that enter in our body, whether it's storage of, for example, oxygen and its transport to our cells. So hemoglobin is a special kind of protein that binds oxygen and is contained in our red blood cells. Whether it's transport of stuff, different chemicals across the cellular membranes, so calcium pump, you can guess it, is a protein, and also a large part of the membrane is also built from proteins. Different communication inside our body, many hormones such as insulin are proteins. That was actually, I think, one of the first proteins for which the 3D structure was discovered. Catalytic reactions, so all reactions in our body are catalyzed, they would not happen otherwise, and the substrate for these reactions is provided by enzymes, so these are biological catalysts that are also proteins, and so on and so forth. So even the structure of our skin is due to a special protein that is called collagen that we lose when we age. That's why we have wrinkles on our skin. So being so ubiquitous, obviously proteins are a common target for drugs. I think, well, don't take me by the word, but I would say that the majority of drugs try to target proteins. And typically the way that it looks like is you look for pockets. So you say that the protein target is druggable. It has a pocket-like hole in it, in its molecular surface, and you try to develop or discover a small molecule that will fit into this hole and will disable some interaction of the protein with some other proteins or some other molecules, and this will disrupt or activate some process and will cure the cause of disease. So unfortunately, many interesting targets do not look like this, so they don't have these holes. And in particular, what is interesting more recently, the pharma industry is interested in what is called protein-to-protein interactions. When you have two proteins that bind together, that attach to each other chemically, and usually their interfaces, they don't have holes, they look flat. And by traditional standards of small molecules, these would be very unlikely to be druggable. And in this case, an interesting approach is actually to develop a drug that is protein itself. So these drugs are called biologics or biological drugs. And a good metaphor here is this lock and key metaphor. So this is due to another Nobel laureate, Emil Fischer, that you can think of some kind of geometric and chemical complementarity between two protein surfaces that make them attach and bind together. And one very prominent application where this kind of mechanism is used is in what is called immunotherapy. So this was recognized by the Nobel Prize in Medicine, in particular for the discovery of what is called program death ligand complex. So it's a complex of proteins called PD1, PDL1. And the idea is that we do develop cancer cells in our body all the time. So why don't we die from cancer? Because most of them are just killed by normal functioning of our immune system. What happens is that cancer cells sometimes express a protein that inhibits the T cells, and this is a necessary mechanism because T cell is stupid. So the immune cells, that's their way of distinguishing between harmful and our own body tissues is this protein that tells don't attack me, I'm a friend and not a foe. And so cancer pretends to be a healthy cell. And the idea of immune therapy, you block some of these proteins. So this is called the checkpoint immunotherapy. And this way you give control back to the immune system, and it allows to destroy the cancer cells. So bottom line, you need to design a small protein or peptide that attaches to either PD-1 or PD-L1 and blocks it for a certain amount of time and gives control back to the immune system. And in this sense, the protein design problem, you can think of it as a kind of inverse folding. So you know how the structure should look like, right? Or at least you know the target, the complementary structure, how it should look like. You try to come up with a sequence of amino acids that will have certain 3D conformation that can bind to this structure. And in this case, methods such as AlphaFold are not immediately applicable because most of these proteins never existed in nature, so you cannot leverage the evolutionary history. So that's why you need to leverage something else. And maybe a simplified and naive way of thinking of proteins that you have, you start with a sequence of amino acids, and the conjecture is that the sequence entirely gives you the structure, and then the structure endows the protein with its function, for example, what it binds to. This is, of course, a simplified picture because you can find proteins that have nearly identical sequence, but a very different structure. So it might be that you perturb just one amino acid and suddenly the thing folds into a different shape. You also find proteins with same structure, but very different sequences that generate this structure. And you can also find proteins that do the same function. They bind to the same thing, but evolutionarily they come from a completely different history, and therefore the structure and the sequence of these proteins is completely different. So they're completely unrelated. And what we conjecture is that you can use actually the geometric structure of the protein molecular surface to predict its function, in particular the binding properties. And this was my collaboration with a group of Bruno Correa at EPFL. We developed a mesh-based architecture that we call MaSIF for protein function prediction, in particular predicting binding. So here you can see an interface score. So this is red tells you that this is where the protein will likely bind, attach to some other protein. And we use this architecture to design de novo or from scratch potential binders or inhibitors for this oncological target PD-L1. So these are the three designs that you see here. They're already confirmed by X-ray crystallography. So we know that they look exactly like this, and we know that they bind. I'm not saying that from here to a new drug that will cure cancer, it's a short way, but it's still interesting direction. So this was a paper that appeared on the cover of Nature Methods last year. So talking about drugs, of course, as you know, developing new drugs is a very long and very expensive business. And one of the reasons is that it takes a lot of time to test that it actually does the right thing, that it attaches itself to the right target. It's not toxic, it's not harmful. It might cure cancer, but also kill the patient. So of course it's not a good drug. And if you look at the space of small molecules that you can, at least in principle, synthesize in the lab, it's extremely large. So I think the estimate is about 10 to the power 60. And of course, this is way beyond anything that you can test in the lab, right? So in the lab, you can test maybe hundreds or thousands or maybe tens of thousands of molecules, right? So now there is also some automation in this domain, and you have high throughput robotic labs that can test, for example, binding of different molecules with high throughput, but it's still a huge gap between the number of synthesizable molecules and testable molecules. So this gap can be breached computationally, and graph neural networks have shown themselves amazingly well in predicting some properties of molecules. And well, it's not surprising again, because as I mentioned in the introduction, that actually there was a parallel history of developing graph neural network-like architectures in the chemical community, and more or less around the same time as graph neural networks started. So some of the well-known architectures, such as message passing neural networks, Justin Gilmer from Google, they were developed with quantum chemistry and virtual screening of drugs in mind. And probably let's say the point where this became already of a level that is interesting for the pharma industry is when the group of Jim Collins at MIT used graph neural networks in this virtual screening pipeline to find antibiotic compounds that can treat antibiotic resistant bacteria. And you may know that this is one of the probably upcoming, if already not existing urgencies in the healthcare field. It's not a question of if, it's a question of when. When we'll have this new infection that defies all our arsenal of existing antibiotics. So I'm actually proud to be a professor at Imperial College, where penicillin was first discovered by Alexander Fleming. So it gave us about a century of remarkable progress in medicine. So the life expectancy that increased dramatically globally is in part, probably one single factor that you can attribute it is the discovery of antibiotics. So we are running out of steam with antibiotics, and you can imagine easily a pandemic that becomes worse than the current coronavirus situation that is caused by bacterial infection and cannot be cured by antibiotics. So long story short, they were able to discover a molecule that was an experimental drug considered for diabetes, but was found not to be effective against diabetes, but it was found to be effective against different kinds of bacteria that cannot be treated with other antibiotics. And this is just one example. You can do a lot of things. So this virtual screening pipeline, it of course depends on the data on which you train. So here it was trained on data of antibiotic resistance. You can also predict a lot of properties. So as far as I know, many pharmaceutical companies are trying to adopt these technologies in their pipelines. So another interesting direction is actually not developing a new drug, because it's very difficult and very expensive and very long, but take an existing drug and try to repurpose it for a different target or for a different disease. And this is what is called drug repositioning. And in many cases, these drugs are taken together in synergy, and what you try to get is some kind of nonlinear effect that will be stronger than the effect of each of these drugs separately, the linear combination. And of course, what comes in this case is some adverse effects. So some combination of drugs might be potentially dangerous and harmful. And there was this beautiful work of Marinka Zitnik, also a postdoc of Yuri Leskowitz from Stanford, where she tried to predict drug-to-drug interactions as a way of basically with graph neural networks that predict edges in this graph. So here there are actually multiple graphs. So there is the protein-to-protein interaction graph that models at a very high level of abstraction the human biology. So proteins are the targets in this case, and how they interact to each other. So there are multiple pathways that if you touch one protein, it will have some kind of ripple effect through this PPI network. Then the drug-to-protein interaction actually explains the mechanism of action of a drug, what kind of protein it binds to. And ideally, in the ideal world, you would like to think of a drug as something that is very precise, that targets just one specific target it was developed for. Unfortunately, this is not the case. And I think on average, again, don't hold me by this number, but something like 40 or 50 molecules are affected by a single drug. So it's only one that you want to target, all the rest are side effects. That's why we're still very far from having this precise therapeutics. And finally, the drug-to-drug interaction is the graph where you don't know the edges and you try to predict them with the graph neural network. And this paper has had a lot of follow-up. So Marinka is now a professor at Harvard at the medical school. And I would like to mention one work that I'm involved in. It's a collaboration with colleagues at Imperial College from the Faculty of Medicine, where we try to take these ideas drug repositioning and repurposing to the domain of food. And when you think of food ingredients, especially from the plant kingdom, they contain a lot of molecules that look like drugs. And it's not surprising that actually many drugs were discovered first in the plant kingdom, and this is also encoded in their historical names. So if you take, I don't know, something as trivial as aspirin, so the chemical name is acetyl salicylic acid, and salicyl comes from the Latin name of the willow tree, the salice. And because this compound was first discovered in the bark of this tree, and people from ancient times knew that if you use the bark of the willow tree, it has an analgesic effect. And indeed, it is now used as one of the popular painkillers, and so on and so forth. So there are other substances, such as, for example, camptothecin. 4 of its synthetic analogs are used as potent anti-cancer drugs, and it also comes from a tree that grows in China. Unfortunately, most of these the compounds that we take together with food, that come with food, they're completely unknown. So if you go to a supermarket and you buy packaged food, you will see the content of proteins and fats and carbohydrates, maybe some vitamins and microelements. You will not see anything about the content of, let's say, flavonoids or indoles or terpenoids and so on and so forth. So these are the bioactive molecules that exist there. Nobody knows how much, which molecules. So it's really the dark matter of nutrition. And many of these molecules, maybe in tiny quantities, they have therapeutic effect that is similar to, for example, anti-cancer drugs. So it is very important to understand which of these foods might have this content. So in our paper, we used GraphML methods to discover these compounds, and of course, well, in order to publish it in anything that would be taken seriously by biologists and medical experts, you also need to explain how to explain your predictions. So that was the bigger part of the work. But probably the coolest part of it is that we collaborated with some famous chefs that took the compounds that we identified and turned them into tasty dishes. And this is Bruno Barbieri, one of the most famous chefs in Italy, and he used the compounds that we identified to cook some dishes for Christmas last year. So I think I like to end my talks on this tasty note, so I will not make an exception here. I hope that you enjoyed the course. It was definitely great for us to teach it for the first time in this way. And I think we made a big journey from symmetry groups to all these exciting applications, from classifying cats and dogs to developing new drugs and even healthier nutrition. So thank you very much. Please let me know if you have any questions about the last part.